Something that you will always see with reciprocating engine is a propeller. You have to have some way to take that raw power that that reciprocating engine has created and turn it into thrust, and then therefore lift as the air goes over the wings of the airplane. The device that we use for that is the propeller. Now you can find propellers on jet engines as well, and we call those turboprops. And technically, a helicopter rotor is still technically a type of propeller. So we're going to cover a little bit of that as well. All right, so to get us started on this, we're going to talk about propeller theory. Like, why does a propeller work the way that it does, and how does it work, and what are some of the little things that we need to keep in mind as we're talking through propellers. Damn it.
Okay, so let's just get started by understanding the propeller parts and pieces, so that way we have kind of a shared understanding as we kind of go forward and talk about some of the aerodynamics that ties into this. Let's start with the center. Every propeller is going to have a hub, and that hub is just going to be the beefiest part of that propeller, where the blades tie into, and then where the propeller then ties onto the aircraft in some way, shape, form, or fashion. Most of the time, it's going to be directly on into the crankshaft of the engine. In the case of like the RVs, there's going to be a gearbox that's there. When we start talking about rotors on helicopters, which is nothing more than a different type of propeller, that's going to go directly onto the hub itself is kind of it's different, and then it's going to come down into a transmission. But either way, the hub is the connection point for all that stuff. Now, on the graphic here, you see that the 8083s put propeller information. That's because you can almost always find the serial number, you can find the model number, all kinds of information that you're going to need whenever you're doing any kind of inspection right there on the hub. Sometimes it's a data plate. Most of the time, it's imprinted into the hub, the propeller itself. It's going to be not necessarily like engraved in, but almost like it's pressed in whenever they cast it. All right, so then we're going to go to the left. We're going to talk about the leading edge and the trailing edge. Now, as we're going to see here in just a second, the propeller is nothing more than just a wing, effectively. It's there to generate lift in the same way that the wings of a aircraft generate lift. It's the Bernoulli's principle. That is just simply going to, as it cuts through the air, one side's going to have a high pressure side, the other side's going to have a low pressure side, and that's going to cause a lifting function. The key difference here is, whereas like the wings on the Piper Cherokee lift it up, the propeller is going to lift it forward, and it's going to want to pull the airplane forward. Then you have the blade tip. That's now blade tips, there's a lot of science that will go into them because of the vortices that get created. Just like the vortices get created on a wing whenever it's developing lift, a propeller will also create vortices. And so, like one of the kind of quintessential examples of this is like the little whisper tip props that drug runners used to run on their planes back in the 70s and 80s, and probably still do now. That was a popular mod that came out that made the plane a lot quieter. Now, obviously, the manufacturer came up with that to keep noise down and like noise abatement, but the drug runners obviously had it for other reasons. The other thing to point out is the back of the blade. Notice that there's nothing really different. It's the blade is just a blade, but notice that there is a twist to the propeller. Now think about this: as the blade descends on one side, it's going to produce lift, want to go the other way, or want to go one way. And now as it ascends on the other side, you're going to have a kind of an interesting dynamic, and we're going to get to that here in just a second. But notice that the twist in the blade. All right, this is a cross section of the propeller. You can see the blade back and the blade face have very different cambers. The reason being is that, like, if you think, remember back whenever we talked about wings, is that air hits that blade. The air molecule that's going to go on the back side, on the blade back, is going to have to travel a lot further, so therefore it's going to go a lot faster. Now, since it goes a lot faster, the pressure is going to be lower, and then as the pressure lowers, the pressure that is, or the pressure on the other side on the blade face is going to stay relatively the same, and it's going to want to push up on the blade, thus causing it to move. The other thing to notice is first off, notice the chord line and notice the difference between the blade back and the blade face. The other one is notice that the angle of attack. Now, whereas a wing, generally speaking, on straight level flight, is attacking the wind straight on, and so the angle of attack is very, very slight. Now that changes based on pitch and all kinds of stuff. A propeller is never that way. A propeller is always going to have a fairly aggressive angle of attack to consider. Now, here in a minute, we're going to talk about different types of propellers. One of them is a constant speed propeller, and the other one is a fixed pitch propeller. Now, this is going to be a constant speed propeller, but I don't want to get into that right now. What I want you to just take away is notice the different things that happen as you start to consider the blade pitch. So we have you'll hear the pilots talk about feathering the prop, powering the prop, like all that good stuff. And I just want to kind of like walk you through what's happening with the pitch of those blades. Now, feathering is like you see on the other on the far left. Feathering the prop basically turns the prop to a 9-degree angle, so it's going directly in there into the wind, and effectively all that's really going to happen is that it's going to cause the propeller to spin as it goes down. You do this to try to reduce the load on the engine, reduce drag, and just let it glide. If you have an engine out, one of the things you're going to do is you're going to feather the prop so that way that propeller is not dragging you through the air. So because effectively you could take a lift creating device and make it a lift limiting device, or drag inducing device, by keeping pitch in the blades. So whenever you hear a prop feather, that's what's happening. And you can also hear it on the ground. And they go to feather a prop, it'll sound wildly different because it's changing the way that lift and therefore the sound is being angled relative to the airplane itself. All right, now power. That's going to be your power range. We'll kind of look at power and flight idle together. You go from 20 to 35 degrees and then 10 to 12 degrees between the two of them. Effectively, power is you're doing exactly that. You're producing power. So if you think about it, think about that yellow prop there as a wing. As the wing wants to produce lift, if that was on an airplane, it would want to push it up, pull it up. All right. Well, and this happens to be that up is directly forward, and it starts to do that. Now, as you increase the angle of attack, the more pull you're going to get. So if you want to do like max power, you're at 35 degrees. That's as aggressive as that blade is going to go, pulling you through the air. So if you're on takeoff, you'll go mixture full rich, props full rich, and then power. You want to get as much power as you possibly can, and that's going to cause the airplane to travel as fast and as aggressively as it possibly can. Then flight idle is like as you climb up and you're on a cruise, you're going to want to pull that power back because you just don't need as much. So just like you can produce a lot of power in first gear in your car, once you're kind of at speed, you want other gears. You go to higher gears to reduce the load on the engine, and then allows the engine to actually, or the transmission, I guess, rather, to turn faster and faster and faster because it needs less and less torque to actually turn the wheels since the car's already going. This isn't really that different. Like once the plane is flying and it's straight level flight, you don't need all that power in the blades, and so you can get a lot of economy just simply by reducing the pitch of the blades, so that way the plane is not having to work as hard, and if it's not having to work as hard, it's not burning as much gas to get the same effect. All right. Ground idle. We'll skip over locks. We're just gonna go to ground idle and then reverse. So ground idle is like whenever you're sitting on the ground at idle, you're not gonna really want to produce a whole lot of lift, and so it's going to be there at 0 degrees. And then reverse is the same thing is happening as it is with the power side, except for you've changed the pitch of the blade so much that it's want to pull the plane backwards at this point. And so you'll see a lot of this on like high-end turboprops like your King Airs, so on and so forth. Whenever they go to land to reduce their landing roll, they'll throw the prop into what they call beta. So they'll put it in reverse, and it'll turn around and slow the plane down a lot faster, and therefore reduce your takeoff roll. Like the Quest Kodiak has a really aggressive beta range, and you can set the plane up so that way as soon as it lands, the plane automatically, once it sees weight on gear, kicks that beta mode in, so that way it really kind of stops the plane. C-130s are another really good one to watch. You can watch videos of these guys landing, and as soon as it hits the ground, you'll hear the engine sound change, or sort of the propeller sound change drastically, and that change in pitch is that those props going into beta, and it'll also go wah, like, because it's now fighting against the relative wind of the plane, and it's causing it to slow down and ultimately stop. Okay, so this is the kind of a layout of the different aerodynamic forces. Now, we've already kind of like talked onto this, but it's good to see the way that this is supposed to work. Now, we've talked about the chord line and the angle of attack and the angle of the relative wind. So the plane is moving from right to left, going through the air, and you can see that the blade is rotating, so that way it hits the wind at like almost a 9-degree angle right there. It's not quite 9 degrees, but it's close. That then is going to produce the lift that's going to make the propeller want to go forward, or want to go up. Well, in this situation, up is directly in line with the way the airplane is going, and therefore that's what produces thrust for the airplane itself. So as that blade spins, it's going to produce that lift. That lift just happens to be in directly in front of the airplane, and therefore we just start calling that thrust. But that's effectively what's happening. And then you have the wings that are doing the same thing. Except for they're laying flat, 90 degrees, to the relative wind. And so whenever it produces thrust, or whenever it produces lift, it wants to pull the plane up. And so really you have a single engine airplane with a two-bladed prop. Basically has four wings. They're just one set of wings is trying to pull the plane up into the sky, and the other one's trying to pull the plane forward. But that's basic propeller theory 101. Okay, so this is just what they're calling like the propeller blade elements. What I want you to see here is notice the aggressiveness of the different parts of the blade. Now, the blade is going to get thicker the closer it gets to the hub, and then it's going to get thinner as farther as it goes out. But also the aggression in the twist of the blade is going to really kind of hit its max. I guess max twist midway through the blade, because that's really what's doing the majority of the work. The tip section has its own vortices management concerns, and then the blade, the hub of the blade, you don't want to produce too much. What you really want more is there, and that area is just structure. You need it to have a good base, so that way you can get the rest of the blade out there, flatten it out really nice and pretty, make it really thin, so that way it grabs the air super effectively. And you can kind of see that from the 12-inch station to the 18-inch station, and you see like that 18 to 42. That's really where the work is happening. And then by the time you get to the end, you're into the tip section, and the blade starts to get smaller. It starts to get less massive, and the pitch becomes almost at a 90 degrees, so it's not producing as much lift, and that's to help curtail some of those vortices and manage the spiraling slipstream, which we'll get to here in just a little bit. Also notice that they say stations on this. Now, for maintenance purposes, a lot of the time you're going to just be inspecting the propeller and you're taking them on and off. You're not going to be doing a whole lot of rebuilds unless you're in a 145 that's what they specialize in, or you're doing NDIs and that kind of thing. For the most part, you're simply going to look at is it leaking? Does it have any damage? Can I fix it? when's the next overhaul going to be at. And the propeller overhauls are generally pretty high. They don't happen that often. And typically, what it means is you just put a new propeller on. You're going to pull it off, send off the old one as a core, get the new one in, put it on. You can't overhaul propellers, so you can send it off. It gets overhauled and sent back to you. But that's that. That being said, the reason why I bring that up now is that whenever you're doing write-ups, if you see like damage at like halfway down the blade, you can say, hey, look, this is at the 21-inch station line. We see this pitting or this corrosion or this damage or whatever the thing is, and that's how you'll refer to it. Now, depending on the type of propeller, you might need to be really specific. Like if you're on a J model of a C-130 and it's like on the number 3 engine, and you look at that blade, there's 4 blades on it, and you say, hey, you can't just say the engine blade has been damaged. You're going to have to go through and say like, okay, it's like on engine number 4 or whatever, on blade such and such, when you have a serial number for that blade on this station, there's this damage or whatever. You have to be really precise with it, especially when the bigger, more complex operations where there's a lot more people. There's a lot more room for confusion, and so to be precise with that, you need to have some sort of naming convention that allows people to be talked directly on to where that damage is at. And using the station methodology is pretty common out there. Yeah, so there's that. Okay, so now let's talk about the forces on a propeller as they progress. First off is what you would think. It's the centrifugal force. Now, centrifugal force is just basically as things spin, that force generally pushes it to the outside, and the propeller is no different. It starts to see this. So you'll see on certain propeller types towards the hub, they'll develop leaks. Those leaks are largely in part because of this, because those heavy propeller blades are constantly being slung around at thousands of RPMs, and that centrifugal force is no joke. It starts to pull on it, and then that just over time will wear things down. It's by far the most dominant force on the propeller. So a lot of these other ones we're about to talk about, they happen, and they make a difference, but not nearly like with your centrifugal force. The next one on B there is the torque bending force. And so in the form of air resistance tends to bend the propeller blades in the direction opposite of the rotation. So basically, as it wants to spin around, those blades want to bend back. Now think about this: like if you have a piece of pipe and you wail on a desk, now as you hit the desk, it's going to want to bend that pipe back. Now, so if it's like a really a high grade copper pipe, you'll be able to hit it, and that copper pipe will just bend over backwards, because like as the pipe went through the air, struck the desk, it hit something hard, some sort of resistance, but the force that's propelling the pipe through the air, namely our fist and arm and stuff, keeps on going, and so something has to give way, and that in this case is the pipe. This is no different. So as the propeller goes through the air is serves a function as a desk. It's something hard. As it hits the propeller blade, the propeller is going to want to bend backwards slightly. Now, you're never, at least I've never seen a propeller that's truly bent out of shape from this. But what is relevant is to keep in mind the stress that's happening on the hub. And these are not really; these aren't small forces, pretty significant, and something to take lightly. All right, then we have the thrust bending force. Now, basically, as the propeller goes around, one of the things that's going to end up happening is going to want a cone. It's going to want to lift off. Now, you can totally see this with helicopter blades. As a helicopter goes to lift off, you'll always know that the pilot's pulling collective, because you'll be able to watch the blades. It'll go from being a flat pitch to also it'll get aggressive, and then as it gets more aggressive, the blades start to curve up on the end. That's called coning. Now, and as the blades cone, eventually it gets to a point where the strength of the blade, the strength of the hub overcome that coning effect, and the blades just start to produce lift, and then lift the helicopter off the ground. the propellers will always experience the same kind of coning effect, but keep in mind they're short. They're generally made of like solid steel, and they won't bend as easily as you would think. However, those forces are still there, still working on those blades. Is something that you have to kind of keep in mind. All right. Then we have the aerodynamic twisting force that tends to turn the blades to a higher blade angle. So basically, as that propeller spins around, the force of the air on it is going to want to make it basically go to neutral. Basically, the air is going to want to push that blade out of the way, and the blade's going to have to push back on it, causing it to produce lift. And so there's this tension that happens. That tension is overcome by the propeller hub, effectively keeping the right amount of pressure on that blade. And we're going to get to how that works here in just a little bit. But effectively, that is what causes the propeller to go forward. That's called the aerodynamic twisting force. Lastly, we have the centrifugal twisting force, which it tends to force the blades towards a lower blade angle. So the hub gets a little bit of help that as it spins around, you have the centrifugal twisting force and the aerodynamic twisting force that are opposed to each other. As they oppose each other, they more or less, they won't directly cancel each other out, but the delta between the two is reduced significantly. Okay, lastly, let's talk about how the propeller is controlled. Now, on a fixed pitch propeller, like you say, like on a Piper Cherokee or something like that, there is no controls. The prop can't change. You can't go into beta or flight idle or anything else like that. It simply just is what it is, and it's attached to the airplane, and off you go. That's all that's all there is to it. Now, with a more complex aircraft, you end up having the ability to change the pitch of of the blade angle on your prop, and that's done through the prop controls. That's usually right there, or it's always right there in the throttle quadrant, next to the throttle and the mixture. If you're in a situation where there is mixture, if you're in a turboprop, there's obviously not going to be one, but or even certain reciprocating engine aircraft, what you can get by without mixture if it's fuel injection. But either way, typically, now this picture, those knobs right there in the center are black, but typically they're blue, and they'll always have the same structure to them, the same shape. It has almost kind of like this like starish, very rigid or very ridged in featuring knob, I guess is the best way to say it. Whereas the throttle is like smooth on the left side. The prop will always be a little bit different, because what they don't want to have happen is to get them mixed up. They're always different sizes. It's very difficult to grab one thinking it's the other. But that's the thought process between having kind of a standardized throttle handle feel between different airplanes, so you can hop in from one to the other without getting confused between the two of them. So whenever you're checking a propeller's functionality, you're going to be in the cockpit, you're going to be running, and you're going to be pushing this handle up and down and watching the manifold pressure come up and down. You'll also hear the sound of the engine will change drastically. Not the engine, but the sound of the propeller will change drastically. You'll be able to hear an aircraft that's running up. It'll be going, and you'll hear whoosh, whoosh, whoosh. Like you'll hear that prop start to go through the different angles and produce different sounds based on that. But inside the cockpit, you're looking at manifold pressure. That's what really will show you how much pressure is that blade is producing.
Now, just like everything else, a propeller is a certificated device, and therefore, if it has a certificate from the FAA, there has to be a data sheet that goes with it, a type certificate data sheet. And you'll remember those from General. Your TCDS will tell you everything that there is to know well, not everything there is to know, but a lot that you want to know about a particular device. The Propeller TCDS will do the same thing for you there.
Okay, so this is a snip from the TCDS off of a Piper Cherokee, and this kind of gives you an idea of the different types of props that you can end up having on a aircraft. So first you have a Cincinnati Model 74 FM 56 or any other fixed pitch wood propeller eligible for the engine power and speed, which meets the following limits. And so you'll see that hey, look, the max permissible throttle setting is like 2400 to 20, but not under 2050. So it could max out at 2400, but never be below 2050. The diameter has to be 74 inches, but not under 70.5 inches. So you think about this. If you have a super lightweight prop, that's all well and good. But if it lets the engine overspeed because there's not enough resistance on the engine to put it in the right RPM range, that's bad. If you have a super duper heavy prop that won't ever let the engine get up to operating speed and it keeps it like say 1900 RPMs, that's also bad. One will cause the engine to basically like destroy itself because it's going too fast, and the other, you'll never get off the ground. You'll probably end up getting just close enough to kind of maybe get in the ground effect, but not really climb yet, and then you end up crashing and killing people. And so that's what it's saying. You also have to think about the operating parameters as you're flying along, as you're doing like your flight planning and saying like, hey, like we're going to go from here to here. This is how fast we can go. This is how much fuel we're going to burn, so on and so forth. All those numbers are based on a standardized set of equipment on that airplane. If you change it drastically, then you're not gonna. Those numbers are going to be invalid, and you're going to end up having people, lost or crashed or whatever. Now, look at the diameter. It says not over 74 inches and then not under 70.5 inches. So we know that in order for it to operate correctly, it has to be at least 70.5 inches across. Like you can't have like a little small propeller up front and have it turning because it's going to just produce a lot of air to cool the engine, but it's not going to be big enough to get over the over the wings and actually get some thrust going, so that way it'll go forward. But then at the same time, it can't be over 72 inches because if it's over 72 inches, then you run into a real possibility of a propeller strike on the ground. If that 72 inch number is calculated so that way if all the struts were collapsed and it was right on the ground, then the prop should still stay well clear of the ground. If you get over 72 inches, then you start cutting into that safety margin, and eventually get to the point where the prop is just right off the ground, and you have serious issues. Now, that's just the first example of a type of propeller that you could potentially use. The next one down is by Macaulay. It's very common. We actually have those. I believe that's what's on my plane, if I remember correctly. But you can see it follows the same sort of limits, except for a little bit more precise. Instead of from 2050 to 2400, now we have 2290 and 2180. That's that range of RPMs that you should be able to see. And then you get down to the other types, the Koppers aromatic, the land plane and ski planes only. So ski planes. So I guess you can't have it if it's on floats. But either way, those are actual part numbers and assembly numbers that could be used. Whereas the other one was fixed pitch blades, so long as it fits correctly and it keeps the engine operating at those sort of parameters, then you're good to go. But whenever you start getting to the more complex props, you get less and less variety to choose from. You get these specific numbers. Now, a lot of aircraft will have just one or two props that can actually be put on it. The Cherokee actually has several that you can do, because this is just like the first three on a fairly decently long list. But there's a lot of them where you can only have one of two props, and that's all. And so that's something to think about whenever you're doing annuals, pre-buys, that sort of thing. Is that hey, look, is this prop authorized for this plane? And you just check TCDS, and after you kind of get some air under your wings, you start to pick up on it's like a lot of them are the same props over and over again. So as long as you see a standard prop, generally speaking, you can be well, rest assured that prop is supposed to go on that engine on that plane. But every once in a while, you'll find some weirdo wacko combination that might throw you off. All right, here's what the actual TCDS for a particular propeller looks like. And you can see there's a lot of data on here to kind of take into consideration. So you have your basic model right there, looking at the main your main table of information. The basic model goes down on the side, and then you can start to kind of go across, and then just start interpolating the data. So from takeoff to and max continuous RPM or horsepower, the diameter, the standard pitch, number of holes in the hub diameter holes, bolt circle, hub dimensions, and the weight. Now all these things matter because, like, if you remember, like, we're just looking at the TCDS on a Piper Cherokee, and it limited the max RPMs to 2,400. Well, this one has 2,800, and so we're gonna say, like, hey, look, this wouldn't work. Either way, this particular propeller, that propeller number, may not be compatible with the with what's authorized to go on to the Piper Cherokee. So you want to set those side by side and look at them. Other things that to take away from this is that it'll tell you the type, material, number of blades up there at the top. So you can see it's a fixed pitch metal, it's aluminum alloy, and there's 2 blades. It's pretty standard GA propeller. You can see the certification basis. It's a CAR 14 certification. You'll see that's pretty common, but like there's other certification bases that you can come across, but that's kind of advanced. We don't necessarily have to go over that. And then the production basis is the production certificate number 1NE. So anytime that something is produced, it's generally produced under a production certificate. And that's a whole like other world when you get to aviation manufacturing. But this is what will tell you, what that production certificate number is. The reason why this may become relevant for you, that like you could have ADs that come out that may say like, hey, like anything that was produced under production certificate X, this has to be done. And so you'd go look at your propeller, you go pull the TCDS up and say like, hey, like which one does this one go to? Typically, they've already done that legwork for you in the AD, but there's always a chance that they didn't, or maybe it's super old. You never know. Then there's other good information here on just the installations. These models are for installation on flange propeller shafts, so like that you can start to see where you have a lot of data that's being produced by these TCDSs, and then you need to make sure that they marry up to each other. Generally speaking, if the TCDS or the aircraft TCDS authorizes that propeller model number, then you're safe. All this work has already been done for you. This is more just trying to develop your understanding of the process, so that way you know kind of what's going on. However, there is always the oddball scenario where, especially as we've seen, Mosaic Bass, and there's all these, the world will probably change, and you'll see a lot more customization in the world of aviation out there, and so these things may become more and more relevant as time goes on. Okay, so this is two things. The more serious one is just always pay attention to the notes on any TCDS. The notes are usually what will get you, because there'll be like some random, hey, look, if you have this number or this number, then don't use this type of bolt, or some rando thing. This is especially true with your O&Ps. I'll tell you, the IA test, this is like the big gotcha section where they will try to trip you up inside of the notes. Like you'll have, it'll say like, hey, look, space the rivets like this, and then it'll be like note 3 is like, unless you're on, this one particular type of airplane, then space them like that, and that will trip you up on the test. So the same thing for your written test and for your oral and practical, you can see the same kind of scenario in there. The other thing I want you to see is that notice that these part numbers are not random. They all mean things, and then the more that you work with them, the more you'll start to understand that, hey, look, that model number actually has given me some pretty solid information. And if I can remember a couple of key things, it will help me out. So like for instance, like the pitch, or hey look, this designates a 5, 4 or 1 1/4 inch spacer thickness. So like I know the spacers that need to go along with this particular prop. Those types of things are really really helpful, and it's impressive. You can sit next to some airplane owner and be like, oh, we see this is this number, this is what this means, and things like that. Some of that's just experience, but some of it is also just knowing it on the front end, so that way you can pay attention to it and know to start paying attention to it as you start to work on more and more aircraft. That those model numbers are really helpful. If you can remember what all the different numbers mean in the different spaces.
Okay, so now that we understand how propellers work, we understand where we get the information about the propeller, let's talk about the design of the propeller. What type of propellers are out there, and like what, how are they different, and why are they different? Why are they designed the way that they are?
Okay, the first and the most simple by far is just the standard fixed pitch propeller. Now, this is just going to be as the name implies, it's just a blade that doesn't change. You can't adjust the pitch of the blades whatsoever. They're designed for the best efficiency at one rotational and forward speeds. It means that like at different speeds, the propeller is going to be less and less efficient. Especially as it's going slower. Now, at cruise RPM, then that propeller is going to be the most efficient. It's going to be the best that propeller can possibly be. So that's what it's going to be optimized for. And there's not that much to say about it. They're very, very simple. The thing that you're going to be looking for whenever you're inspecting them is like, what's the leading edge look like? Has it caught a rock or whatever? Do we need to blend that down? And is there any cracks or corrosion? That being said, I don't think I've ever seen corrosion on a prop that I can remember, at least. Maybe on certain ones you might get some oxidation here or there, but like for the most part, I can't remember seeing corrosion on anywhere. Cracks you'll get every once in a while. They're not really that common, generally speaking. These things are designed pretty well, and they're kind of like a no failure point, because it's just a piece of metal at the end of the day. Most single engine aircraft use fixed pitch propellers. The constant speed propellers are actually probably the more rare version or type of propeller that's out there. But yeah, so that's really that's it. It's pretty straightforward. Okay, another honorable mention almost is the Test Club propeller. This is literally just there to test the strength and output of an engine. You'll hook it up, it'll start to run, and this just simulates the load that could potentially be placed on an engine that's operating at max RPM, going through the air. They use it to break engines in, and then to test the power output of an engine at speed. Now, that being said, you'll very rarely encounter these, if you encounter them at all, but they are out there, so something for you to be aware of. Okay, so the other big category of propeller that you'll come across out there is what they call a constant speed propeller, or a variable pitch propeller. Now, this is going to be on complex aircraft, so like your Piper Cherokees, your Cessna 172s, your RV-12s, they all have fixed pitch propellers. But then as you start to graduate into more complex aircraft, more capable aircraft, you start encountering these constant speed propellers. Now, what is a constant speed propeller fundamentally? All right, now the propeller has a natural tendency to slow down as the aircraft climbs up, and the speed up as the aircraft dives, because the load on the engine changes. So think about it. As it starts to climb up, it's having to work harder and harder and harder, which will slow the propeller down. But wherever it dives, you have gravity working with you. So instead of having like that, trying to push the rock up the hill, now the rock is pushing you down the hill, so you're going times two faster in a dive, which then makes the propeller want to spin faster, because the air is going over it that much faster. So to provide a efficient propeller, the speed has to be kept as constant as possible, and so they came up with a device that will allow for the propeller to change pitch based on a certain setting inside of the cockpit, and then adjust as the plane goes up or down or whatever. So this device is called the propeller governor, which we're going to talk about here in just a minute. But by using propeller governors to increase or decrease propeller pitch, the engine speed is held constant. So that way the propeller doesn't overspeed the engine or drag it down or anything else like that. It's always right there where you want it. That's why we measure it in manifold pressure. We set it to a certain manifold pressure, and that manifold pressure has to keep. Okay, so here's an example of a constant speed propeller on a King Air. The If you had a fixed pitch propeller on this in particular aircraft, it would be highly inefficient, and you would lose a ton of performance on it. You'd also not be able to get into half the airstrips because you would, for one, have to get the engine up to speed and then get the aircraft up to speed for the propeller to produce enough power to get it off the ground, produce enough lift or thrust to get off the ground. And then you would be dragging in the air at certain air speeds. And then whenever you landed, you'd have to have an elongated rollout because you wouldn't be able to feather that prop or put it into beta to slow you down. And so you can see the advantages of those constant speed propellers become pretty drastic, especially on your higher end aircraft that are capable of a lot more. And so being able to tailor that prop angle is really essential to operating these more capable airplanes. Now, one of the other it's not necessarily its own independent type of propeller, but it is an independent feature of propellers. Its ability to feather. Now, feathering essentially is whenever the blade will go to a 90 degree and have like the least amount of resistance against the forward air. The relative wind, I guess is the right way to say it, as possible. So they do this so that way if an engine were to fail, you should be able to feather it and reduce the drag of that prop on the aircraft and allow you to get on the ground. Now, think about this. Like if you have like a Baron and you're flying up, so you get two engines, one on the side of the other. If all of a sudden one engine fails, and now that prop, instead of producing thrust, starts to produce a large amount of drag, it's going to make that plane want to yaw pretty significantly. If it yaws significantly, then you can get to the situation where it's almost impossible to operate, and you end up crashing because of it. By allowing that prop to feather, then you get rid of that whole thing. It'll still want to yaw because the prop's still out there, still catching the air, but it's not going to be doing it nearly as much because the blades are flat instead of being, or they're laid horizontal rather than being vertical, catching every bit of air that comes across. So almost all of these small feathering propellers use oil pressure to take the propeller from a low to a low pitch, and uses blade, flyweights, springs, and compressed air. And we'll talk about all this stuff here in just a minute when we start talking about propeller governors, and it'll make more sense. But on the feathering propellers, they have these latches that will lock the blade into place. Now, these can be internal or external and are contained within the propeller hub. In flight, the latches are prevented from stopping the blades from feathering because they're held off of their seat by centrifugal force. As the blade spins, it pulls the latches up so that way the blade can move freely. Now, latches are needed to prevent excess load on the engine at startup, and if the blade were in the feathered position during engine start, the engine would be placed under an undue load during the time when the engine is already subject to wear. So, long story short, there are latches in there that will allow the prop to feather and will keep it from moving into the right scenario. However, the latches are prevented from latching if as long as a centrifugal force is applied.
Okay, now let's talk about the constant speed propellers and the governors that allow them to maintain a constant speed, and how do they work, and what is the maintenance requirement for us as airframe and power plant mechanics?
Okay, so how does a constant speed propeller work? Well, at the heart of that is the propeller governor, and you're looking at one right here. Now, a propeller governor is an engine RPM sensing device and a high pressure oil pump. In a constant speed propeller system, the governor responds to a change in engine RPM by directing oil under pressure to the propeller hydraulic cylinder or by releasing oil from that hydraulic cylinder. The change in oil volume in the hydraulic cylinder changes the blade angle and maintains the propeller system RPM. The governor is set for a specific RPM via the flight deck propeller controller, that was the handle that we were talking about, which compresses or releases the governor's speeder spring. So you can look at this governor, and you can kind of start to put together in your brain how it all will work. So you have the adjusting rack connected to the pitch control. There's the speeder spring they were talking about that pushes a certain amount of pressure on those flyweights, and then you have the governor pilot valve that you can turn around and adjust that valve to get the right level of manifold pressure that you want. And then you have the oil pump that actually produces the oil that's going to then push on the that hydraulic cylinder. It's going to make this whole thing work. And then at the very bottom you have a direct gear drive from the engine, so it basically attaches directly to the engine and then operates that way. So let's look at a cutaway to see if we can make this make more sense. All right, here's a cutaway, and we're just going to walk our way through it. All right, so the engine-driven single-acting propeller governor, which is our constant speed control here that we're looking at, it receives oil from the lubrication system. So the engine oil goes into it, and that's what provides the power to make all this work. As it boosts its pressure that's required to operate the pitch changing mechanism. Okay, now that speeder spring that we talked about opposes that governor's flyweight's ability to fly outward during turning. So as the propeller spins, the flyweights want to fly out. Well, the speeder spring pushes down on it, then it prevents them from doing that. So in order for the flyweights to get out, the propeller has to go faster and faster and faster to increase the amount of centrifugal force that's on those flyweights to overcome the spring tension of the spring itself. And so there's two numbers there. So remember, like Newton's second law, like force is equal to mass times acceleration. So the mass of the flyweights aren't going to change. They're fixed. However, the acceleration can. So the faster they go, the bigger that force number becomes, whereas the spring tension is constant. And so that allows us to play against those two against one another and get those flyweights in a certain position. As those flyweights change position, it also helps change the blade's pitch. Now, this action between the two of them moves the pilot valve in the governor to release oil from the propeller piston and allows the blade flyweights to increase blade pitch, which increases the load on the engine, slowing it down or maintaining it to a set speed. So essentially, as those flyweights open up, or they start to move outward, then they get more and more oil that helps produce greater pitch in the blade. It actually helps to turn those blades as needed. However, if you were to slow down, the speeder spring gets more of an advantage, which causes the flyweights to come in, which then reduces the amount of oil, which then turns around and goes to reduce the amount of pitch that is on those on that prop. Now, the speeder spring above the rack opposes the action of the governor flyweights, which sense propeller speed. If the flyweights turn faster than the tension on the speeder spring, they fly out. This is an overspeed condition. All right. To slow the engine propeller combination down, the blade angle must be increased. Oil is allowed to flow away from the propeller piston, and the flyweights increase the pitch and blade angle, slowing the propeller until it reaches an on-speed condition where the force of the governor flyweights and the tension of the speeder spring are balanced. The balance of the forces can be disrupted by the aircraft changing altitude or the pilot changing the tension on the speeder spring with the propeller control on the instrument panel. So essentially, the flyweight and the speeder spring want to be balanced. If they are unbalanced, then bad things end up happening, and then that can happen from a variety of different factors weighing in on the aircraft. Well, it suffices to say for right now, you have the tension of the speeder spring that's pushing down on those flyweights. Those flyweights are then controlling the amount of oil that comes into into the governor, and then turns around and is going into a hydraulic pump or hydraulic cylinder, which then is actually turning the blades manually one way or the other. Okay, here is a graphic to kind of help us visualize the what's happening between this speeder spring and the flyweights. Now, the flyweights, whenever they are on speed, meaning that they are doing exactly what they're supposed to do, they should be flying, directly at a 90 right there. And notice the position of the pilot valve. It's set exactly, like nice level. Everything is as it should be. Okay, this is an overspeed condition. Notice the flyweights are starting to head outward. Like the prop is starting to spin faster and faster, so that you're getting more and more of that acceleration, which is creating more force that the flyweights can then push on the speeder spring, which then in turn opens that pilot valve up a little bit more. So as that pilot valve opens, more oil can come in there, and then you start to get a greater amount of pressure that's placed on the blades themselves, because this is eventually going to feed into the hydraulic cylinder, which then causes those blades to turn. Now, I think about it, as the blades start to turn, they're grabbing more and more air, so that pressure is coming up and higher up. So that way, it's then starting to naturally start to slow it back down. As it starts to slow it back down, you'll eventually get back to an on-speed condition. Okay, so this is a underspeed condition. Notice that the speeder spring now is in the dominant position. It's pushing that pilot valve down. And it's cutting oil off. Now, as that ends up happening, then there's less pressure on the blades to turn into a more aggressive position, and then the wind is starting to push those blades back. As the wind pushes the blade back, then it's going to naturally start to speed up, now, which will eventually right the underspeed condition to where it gets back to on speed again. But those are the kind of the three ways, the three conditions in which the governor could actually be happening. This is a really simple, graphic, but it kind of shows you. Notice that we haven't changed the pilot control the entire time. Now, as the pilot control changes, it's going to change the amount of spring tensions there. As that spring tension changes, then you're going to induce an overspeed or an underspeed condition, and then the natural process will happen until we get back to on speed again, to all where the flyweights and the speeder spring are balanced once again. And so you can see how it's actually a pretty beautiful little system, because it's just using very basic physics to control something that's actually fairly complex. And like it will stay that way, like that engine speed, that manifold pressure will stay consistent because of the propeller governor that has this going on up in the hub. Okay, so now let's look at the two kind of subsets of constant speed propellers out there. You have feathering and non-feathering. Let's start with the non-feathering first. So the basic hub and blade retention is common to all models that we're going to be talking about. The blades are mounted on the hub spider for angular adjustment, and the centrifugal force of the blades, mounting to as much as 25 tons, is transmitted to the hub spider through the blade clamps and then through the ball bearings. The propeller thrust and the engine torque is transmitted from the blades to the hub spider through the bushing inside of the blade shank. In order to control the pitch of the blades, a hydraulic piston cylinder element is mounted at the front of the hub spider, and the piston is attached to the blade clamps by means of a sliding rod and fork system for non-feathering models, and a link system for all feathering models. The piston is actuated in the forward direction by means of oil pressure supplied by the governor. So it means that the more that pilot valve opens, the more pressure gets pushed on those blades, causing them to turn, and then the less that the propeller governor or the pilot valve is open, the less tension or less oil pressure is put on it, causing the blades to turn back the other direction. The piston is actuated in the front forward direction by means of oil pressure supplied by the governor, which overcomes the opposing force created by the flyweights. Hartzell and Macaulay propellers for light aircraft are similar in operation. The manufacturer's specification and instructions must be consulted for any information on the specified models. So essentially, we understand how the governor works. How the blades turn all comes down to the amount of pressure that's being pushed on by this hydraulic piston, and it's pushing down on these springs. As those springs compress, the blade will turn because they're locked into where those springs are at. As the springs relax, the blade turns back in the other direction as that propeller piston starts to recede. Okay, so here's an example of a feathering propeller. So feathering is accomplished by releasing the governor oil pressure, allowing the flyweights and the feathering spring to feather the blades. So it means basically when you set it to feather, it's going to release all the pressure, and the feathering springs are going to kick in and then feather the blade into place. Now this is done by pulling the condition lever back to its limit of travel, which opens up the port on the governor, allowing the oil from the propeller to drain back into the engine. Feathering occurs because the summation of internal propeller forces causes the oil to drain out of the propeller until the feather stop position is reached. The time necessary to feather depends upon the size of the oil passage from the propeller to the engine and the force exerted by the spring and the flyweights. The larger the passage is through the governor and the heavier the spring, the quicker the feathering action is, which it can be pretty quick. And a elapsed time for feathering between 3 to 10 seconds is usual with this system. Engine shutdown is normally accomplished during the feathering process. So essentially, you're going to pull the prop back to feather. It's going to expose a port, which is going to suck all the oil out of there. And now at that point, there's no pressure being pushed on that hydraulic cylinder to cause the blades to have any bite in them whatsoever. And so the flyweights that are usually external attached to the blade themselves are going to kick into gear and cause the blade to go into a feathered position. Okay, so now on the ground, if we needed to unfeather a prop, there's a bunch of different ways we could do this. There's three, rather. We could start an engine so the governor can pump oil back into the propeller and reduce the pitch. So we just start it up, adjust the propeller controls, and that will cause it to happen. Another way is to provide an accumulator connected to the governor with a valve to trap an air oil charge when the propeller is feathered, but released to the propeller when the RPM control is returned to normal position. This system is used with training aircraft because it unfeathers the propeller in a very short time and starts the engine windmilling. And that's what you see here. And then lastly, you can provide an unfeathering pump that provides pressure to the force of the propeller back to a low pitch quickly using engine oil. So in short, what ends up having to happen to unfeather the engine is that you have to return oil pressure in some way, shape, form, or fashion back into the prop, causing the blades to actually turn back into position.
Now, for those propellers that are attached to turbine engines, there's a certain thing that can happen where you reverse the pitch. So if you want to cut down your landing roll, you can reverse the pitch and put it into a beta range that causes air to go forward instead of backwards. Now, this weird I guess attribute of a turboprop is pretty handy in a lot of situations. So let's talk about how that works and what that means for us.
All right, so we understand how a propeller governor works now. Let's talk about the beta rods and how they factor in. So low power, the propeller and the governor flyweights do not turn fast enough to compress the speeder spring, as we've learned. Now, in this condition, the control valve moves down and the high pressure oil pushes the dome forward, moving the blades to a low pitch. Any further movement pulls the beta rod and the slip ring forward. So, meaning if you reduce the propeller down to its lowest level, you're going to hit this point where the propeller is basically not producing any thrust whatsoever. All right, and at that point, the governor is sitting with the flyweights perpendicular. The pilot valve is closed. Nothing is really happening. But if you continue to go, you're going to now pull up the beta rods, and you're going to introduce a whole new series of operations to get the blades to go backwards. Now, the forward motion of the slip ring is transmitted to the beta valve via the beta lever and carbon block. Forward movement of the beta valve stops the oil supply to the propeller totally. This prevents the blade angles from going any lower, and the primary blade angle and is the minimum blade angle allowed for flight operation. From this point, the propeller is in beta mode. If the engine power is reduced when the propeller is at the primary blade angle, the propeller speed decreases since the blade angle does not change. Now, let's look at this. Alright, now the lock pitch solenoid valve prevents the propeller from going into reverse or below the primary blade angle in the event of a beta system malfunction during flights. It's fail-safe to make sure that all of a sudden the propeller doesn't slip into beta while you're flying along and cause the plane to basically do a flat spin. Now, the solenoid is energized by a switch mechanically connected to the propeller slip ring linkage via a second carbon block. As the oil pressure leaks off around the propeller shaft oil transfer sleeve, the blade angle slowly drifts back towards high pitch. This deactivates the low pitch solenoid valve and restores the oil supply to the propeller servo. The low-pitch solenoid valve cycles, closed and open, as a backup to the valve function. Moving the power lever backwards causes the reversing cam and cable to move the beta valve backwards, allowing more oil to flow into the propeller dome, causing the blades to go towards a reverse pitch. Effectively, once you hit that beta range, you're causing the exact same thing to happen, except for now the beta rods are exposed, and like you have oil pressure entering the beta rods, which then continue to push those propellers to go all the way back to the stops, putting you into reverse mode. Now, once it's reversed, once it's in beta mode, the propeller speed is no longer controlled by changing the blade angle. It's now controlled by limiting engine power, bringing the propeller lever to feather position causes the speed selection lever on the CSU to push the feathering valve plunger and allows the propeller servo oil to dump into the reduction gearbox sump. The pressure loss in the propeller hub causes the feathering springs and the propeller flyweights to feather the propeller, bringing it out of beta mode. All right. In the event of the propeller overspeed not controlled by the propeller overspeed governor, the flyweights and the propeller governor move outward to the speeder spring cup contacts reset lever. The movement of the reset lever around its pivot points opens the pi air passage. The pi bleeds into the reduction gearbox by limiting the fuel supply to the engine. This prevents the propeller and power turbines from accelerating beyond 100%. 6% RPM. Now that's a lot to basically say that like once you're in beta mode, like you're in beta mode, it's there, and then you're going to use the engine speed to determine how much thrust you have going forward. If you want to bring it out of beta mode, you simply grab the levers, come back up. That will then cause the propeller governor to allow all the engine oil to dump back into the sump, and then it will allow the flyweights and the springs to feather the blades, and then you can come back in with pitch to get going again. It sounds really complicated. It's actually fairly simple, fairly straightforward once you see it in action. So in class, you'll be able to work through a lot of this.